Yeah, thanks a lot for inviting me. I'm really happy to be here. I'm sorry I couldn't be there in person, but yeah, excited to be here. Um, right, so I'm going to be talking about data-driven and data-assisted modeling for applications in fluid dynamics and geophysics. I'm a postdoc at Lawrence Berkeley National Lab. So sort of to give a sort of short introduction, which is not really necessary for this audience, but modeling the state of a fluid dynamical system is a really important task for many scientific applications, such as numerical weather prediction and climate modeling. But it is inherently difficult due to the mathematically chaotic nature of turbulent fluid flows, and because there are several hierarchies of interacting scales within a system. And as an outline, I'm going to be the first part of my talk will be talking about purely data-driven ML modeling approaches and the limitations of those approaches. And in the second part, I'll be talking about possible ways to implement a data-assisted or hybrid modeling of fluid flows for both fluid dynamics and numerical weather modeling. So just to sort of give you a brief introduction, so when I talk about data-driven machine learning models, I'm talking about like purely ML-based models that attempt to like construct a mapping between the history of the flow fields to the future. And there's several, if you might notice, there's several different configurations in which people do this, where the ML model might be recurrent, it might be convolutional, it might be a state-of-the-art ML architecture, but typically the format is remains the same, which is you're trying to create a mapping between the historical states of the dynamical system up to the present time t, and then try to use the machine learning model in a supervised way to predict the next time step, which is get x t plus tau at some time t plus tau in the future. In this case, the machine learning model has to learn a time stepping function, and such machine learning models which need to learn spatial and temporal dependency can be difficult to train at scale, as we will see in the next part of the talk. The computational cost of training pure machine learning fluid dynamics models can be really high for all but the simplest of problems. And for example, so far there have been a lot of impressive advances in the development of data-driven models of the Earth's atmosphere, but these models don't currently match the accuracy of state-of-the-art physics-based general circulation models. And in terms of short-term forecasting of chaotic dynamical systems, we showed a few years ago that you can use a recurrent machine learning model to forecast the state of a chaotic or of a low-dimensional chaotic dynamical system, which is in this case, this is an example of the Kuromoto-Swishinsky equations, which are one-dimensional PD that shows spatial-temporal chaos. And as we can see that the machine learning model can predict the true state of the Kuromoto-Swishinsky system really well for a non-trivial period of time, which is, in this case, it's about 5 multiples of the Lyapunov exponent or the Lyapunov time, which is 1 over the Lyapunov exponent. And that's really a nice result. And we also showed that if you have a high-dimensional chaotic dynamical system, then you can use model parallelization. So you can use, if you are trying to predict, for example, a one-dimensional grid, so you're trying to predict the state of a dynamical system, which is a spatio-temporal system from t to t plus 1. In this case, the bottom is the current state, and the top grid is the future state or the prediction of the current state. Then you can divide your domain, in this case, which is a one-dimensional domain, into separate parts, so like decompose the domain, and then use independent machine learning models to predict each separate section of the domain with some information flow between adjacent models, so as to enable local information transfer for modeling local interactions. So in this case, we are imposing the fact that there are no long range interactions in this fluid dynamic in this PDE system, and we show that in a couple of papers that it can be really efficient for predicting the state of a very high dimensional chaotic dynamical system. And this work can also be extended to general circulation models for numerical weather prediction with machine learning. And our collaborators, Troy Arcumano and Istvan Sunyog at Texas A&M University, showed that the parallelized ML configuration that we introduced can emulate the full state vector of certain variables of the global atmosphere in a simplified circulation model with forecast skill that's comparable to the physics-based model out to about 4 days. So in this work, basically, the machine learning model was learning to emulate a simplified circulation model called SPEEDY. And what we were able to show was that the machine learning model has comparable accuracy or comparable forecast to the physics-based model out to early, out to 4 days. These plots are showing the northern hemisphere temperature at 24, 48, and 72 hours, the root mean square error at several vertical levels, and we see that the ML model and the speedy model have comparable RMSE scores. Now, the next part I'm going to be talking about some of the recent work that we are currently in the process of doing, which is high resolution forecasting of surface wind speeds. So for this part, we've chosen to forecast 12 variables from the ERA 5 reanalysis data set, and we're going to be trying to forecast them using machine learning at the 0.25 degree lat long resolution. The reason we've chosen like surface wind speeds is because surface wind speeds have a lot of fine scale detail. Forecasting of surface wind speeds could have really useful applications in, for example, wind farms, where you might need to know what the electricity output is going to be for the next day or the next several days. So this is an important problem to tackle. So we are mainly interested in forecasting the surface wind speeds, which are the U10 and V10 variable, the 10-meter surface wind speeds, wind velocities. But in order to be able to predict them, we are basically jointly predicting 12 of these chosen variables together to increase the forecast skill of the model, where you have wind velocities and the geopotential at a few different chosen vertical levels in the atmosphere. We use 40 years of training data, which is from 1979 to 2015, sampled at 6 hourly intervals. And this leads to a pretty large training data set size, 3 terabytes. It's large, but it's not as large as it could be. Like if we were to choose to forecast, for example, all available vertical levels and variables in the ERA 5 data set, we could easily go up to 50 or even 100 terabytes, which is a really difficult sort of computationally challenging problem. And the goal is to like keep improving this sort of forecast model, as well as the amount of data our model can process, and get better and better forecasting results. The ML model that we are currently using is called the Fourier neural operator, which was developed by Zhongyi Li and his collaborators, supervised by Anima Anandkumar. So the configuration is fairly straightforward. We use the ML model, which is the Fourier neural operator, to predict a single step into the future. So from x of t, we train the ML model to predict x of t plus t tau, where tau is 6 hours. So a 6-hour increments of prediction, and the input is 12 variables at the 720 by 1440 resolution, and the output is again the same 12 variables at 720 by 1440 resolution, just at 6 hours into the future. And this is going to be run iteratively after being initialized with a certain initial condition. The training is performed using state-of-the-art NVIDIA A100 GPUs, and in this case, we use 256 GPUs to train the model using a distributed data parallel approach. The training was performed on the new Perlmutter HPC system at NERSC at LBL. And this problem basically highlights the computational cost of training large, purely data-driven models. I want to highlight my collaborators on this project. This is still ongoing work, but Sanjeev is the youngest member who did some really nice work over the summer at LBL, where he was a summer student. I want to particularly thank Karthik for putting together a lot of these collaborators, and Anima for supervising us. So let me show you with that. Also want to point out that Sanjeev is an undergrad at the University of Michigan, and he's applying to grad school. So if you want a stellar grad student, definitely consider hiring him. So with that, I want to sort of show some results, which is some preliminary results that we have for the high resolution forecasts of surface wind speeds. I'm going to play this movie. So basically, the top panel is going to show you the predicted 10-meter wind speed, which is calculated by putting the predictions of the U10 and V10 variables together by just calculating the speed from the velocities. And the bottom panel is the true 10-meter wind speed. And this is the ACC curve. We see that we get reasonable accuracy up to reasonable anomaly correlation coefficients up to between 60 and 80 hours. Let me just play this video real quick, and you'll see that what we see in this is that the large scale features are really well captured. Our model still misses a lot of the small scale features. If you look at zoom into like smaller regions on the surface of the Earth, we still don't get as much accuracy as we would like. What's interesting is that a lot of the large-scale phenomena are captured pretty well up to even 60 hours into the future. So yeah, there's a lot more work to be done in this case, but it's a good start. And this sort of like inspires a sort of broader question, which is, why use machine learning at all when physics-based numerical models perform really well, and machine learning takes a large amount of computational resources and time to train. And one of the sort of like one of the answers is that the inference time for machine learning models is several orders of magnitude faster as compared to numerical models. Right now, it's not a very fair or accurate comparison, but if we were provided we were to get accurate, we were able to train accurate machine learning models, then it wouldn't be surprising if the inference times for getting a forecast using a trained machine learning model were 10,000 to 100,000 times faster than numerical physics-based models. Yeah, that's provided we can get the accuracy to be comparable or to physics-based numerical models. But in the shorter term, machine learning could be really useful for generating huge numbers of ensembles of forecasts that could work in conjunction with physics-based models, either for data assimilation or for forecast uncertainty quantification. Yeah. With that, I want to sort of move on to the next part of the talk, which is data-assisted forecasting. So what we saw is that even with parallelization, model parallelization and data parallelization, if the system is very complex, then a purely data-driven approach might require a prohibitive amount of training data or computational resources. But in many cases, we may have partial knowledge of the dynamics, and certainly in the field of numerical weather modeling, we have a really good knowledge of the dynamics, and we are able to have a really good physics-based model. But if we were, for example, to run a physics-based model that's lower in computational cost than the operational models, then you can have an imperfect physics-based model, which doesn't resolve all the features fully, or it doesn't resolve all the physics completely. Then this motivates the question of can we build a hybrid data-assisted model that combines machine learning with an imperfect knowledge-based model? And basically, data availability and computational resource constraints suggest that a hybrid approach, where a physics-based numerical solver works in tandem with a coupled machine learning architecture, which leverages the strength of each approach, could have a reasonable computational cost while still maintaining good accuracy. So the basic comparison is that on the one hand, you have a purely physics-based model where you use a PD solver or a numerical model to time step from the state of a dynamical system from x at t to x at t plus tau. Now, on the other hand, you might try to train a machine learning model that tries to train a neural network to take the state of your dynamical system from x at t to x at t plus tau. The question is there a way to combine these two and create a hybrid model? And when we talk about hybrid machine learning and PD approaches, then there are many excellent approaches which can be regarded in this category, which can be categorized as hybrid models, and that includes physics-informed neural networks. There's some really nice work on learned discretizations. Then there's ML parameterized PDEs, and all of these are like really nice techniques. The approach I'm going to describe now attempts to build an ML augmentation on top of existing models, such as general circulation models for atmospheric science or CFD models for fluid simulation. So the main sort of benefit of this approach is that it does not assume that we need to write new models from scratch, or that the physics-based models are differentiable or able to backpropagate, or that we are able to backpropagate through them. So oftentimes, when you're working with models that have had years of development behind them, it's a really difficult task to be able to rewrite them in a language which accommodates differentiability, or making sure that the models are differentiable. So this approach could have several advantages in trying to build ML models on top of existing physics-based models. The approach itself is fairly straightforward. We introduced it in a paper in Chaos a while ago, so where you have a low-cost, inaccurate physics-based model which time steps your state x of t to x tilde at t plus delta t. So what your low-cost physics-based model is essentially a reduced accuracy, cheap model that is used for time stepping, which gives you an initial or preliminary estimate x tilde at t plus delta t, which is the forecast of the system at t plus delta t. And then you use machine learning on top of that to correct your estimate x tilde to give you an ML estimate of the corrected state at t plus delta t. And the hope is that the combined machine learning and physics-based model is either as accurate or more accurate than a high-cost or accurate physics-based model. We showed that this was true for a large number of low-dimensional dynamical system and even high-dimensional dynamical systems with a few spatial dimensions in our paper. But I'm going to be talking about this sort of hybrid MLPD approach for fluid modeling in the next few slides. When we talk about fluid modeling, the computational cost of a simulation for a given fluid modeling problem is typically directly related to the resolution requirements. These are in turn determined on one side by the Kolmogorov length scale, because your the size of your grid has to be fine enough to resolve the smaller scale features, and on the other hand, your grid has to be large enough to fully cover the domain. So that sort of predetermines what the resolution requirements are for your problem. But one might think, like one way to accelerate a simulation might be to run it on a coarse grid, which does not resolve the fields fully. And obviously, since there's no free lunch, this results in an imprecise or incomplete simulation. The key idea that we explore is to use machine learning to correct an under-resolved trajectory. And it's important to sort of note the differences between like fluid modeling and image processing. It's not sufficient to simply post facto super resolve a low resolution trajectory with machine learning, and that's mainly because the low resolution simulation and the high resolution simulation follow different trajectories. There are nonlinear interactions across length scales, and the dynamics at the small scales interact with the dynamics at large scales and vice versa, which leads to completely different trajectories for the low res and high res simulation. As this cartoon tries to illustrate, the trajectory of a low-resolution CFD simulation is not simply a downsampled version or a mapping of a high-resolution trajectory. It's in fact a different trajectory altogether, even if you start with very similar initial conditions. With this background, I'll describe the hybrid architecture that combines deep learning with a PD solver. So mainly, you have the assumption that you have a high-resolution PD solver, which is a PD time stepping scheme that's accurate, but it's expensive. And you also have a low resolution PD solver that takes your quotient fields small x at t to small x at t plus tau using a low resolution PD solver, which is imprecise, but it's cheap. Now, how do you recover capital X at t plus tau, which is the field that you would have obtained if you had used a high resolution solver instead of your low resolution solver? And the solution here is that you choose a time step tau, which is very small compared to the largest eddy turnover time or whatever the natural time scale of the system is. So you have a really small time step or a time interval. And at these small intervals of time tau, you basically take the output of your low resolution PD solver and correct it using a machine learning model. So you first naively interpolate it to the required resolution and then use a trained machine learning model to estimate the error in the simulation. So the error is basically what determines the difference between what x tilde and x, which is what you would have obtained if you had used a high resolution PD solver instead. And the error is added back to the interpolated fields to give you an ML estimate at t plus tau. And in this hybrid, the full architecture, what happens is that you have a low resolution PD solver which solves the system at a lower resolution while saving computational cost. And then you add at intervals of time tau, you add an ML correction to the output of the low resolution solver to get a ML estimate x ML at t plus tau. And if everything works well, then you are able to get an ML estimate of the high resolution fields by still running a low resolution solver. And basically what the architecture is doing is it's something that's more sophisticated than simply super resolving the low resolution trajectory. What it's doing, as is illustrated in this cartoon, is nudging the low resolution trajectory towards the correct high resolution trajectory by correcting the physics of the low resolution simulation at short intervals of time. So capital X of t is a trajectory, the ground truth of the high resolution trajectory, and small x of t is what the trajectory would have looked like if you had not applied any machine learning corrections. But if you do apply machine learning corrections, then what you're doing is you're simply nudging the trajectory closer to the high resolution trajectory by applying these corrections at short intervals of time tau. And we basically built an initial prototype using Daedalus, which is a Python-based CFD solver, and we tested it on a Rayleigh-Bernard convection system in the moderate Reynolds number regime. So the inputs to the machine learning model in this case are these 128 by 128 outputs of the low-resolution PD solver at time intervals, small time intervals tau. These are the velocities and the temperature and the pressure fields. These are input to the model, and the model outputs the model error corrections at high resolution, which it has learned by looking at some training data on different trajectories. And these model error corrections are applied to the output of the low resolution solver in order to get an estimate of the high resolution solver, or what you would have obtained had you used a high resolution solver instead. And what we find is that, after running the simulation for 100 steps, or which is about 280 turnover times, we see that our architecture captures the high resolution spectrum really well. So in this spectrum, you're looking at the spectrum of the variable, the temperature variable. And what you see is that on the y-axis is there's a huge, the spectral density, but there's a huge range of scales in the spectral density. The numbers are going from like 2 to the power 25 to 2 to the power minus 23. And your ground truth is the green line. Your MLPD solution is able to recover most of the missing scales in the low resolution simulations, which is denoted by the blue line. And we still do miss some of the smaller scales, and this is a problem that we haven't really been able to fix. But the point is that there's not too much energy in these small scales, just because of how small these numbers are compared to some of these numbers, and even in the intermediate scales. And we also compare the RMS error curves between the MLPD solution and the baseline low resolution PD solution, averaged over 20 initial conditions. And what we see is that the ML corrected solution has an RMS error that grows slower than the baseline solution. So what we're obtaining is that we're running a low resolution solver while getting more accurate results than we would have obtained if we hadn't applied the machine learning corrections to the low resolution solver. And if you look at the visual results, we see that there's a lot of significant differences between the low-res PD output, upscaled or interpolated naively, and the ground truth, whereas the MLPD solution captures a lot of the small scales to medium scale features a lot better than what the low-resolution solver was able to obtain. I won't spend too much time on this, but this work has also been extended sort of to sort of a hybrid numerical weather prediction model, which also has been led by Troy and Istvan at the Texas A&M University. What they do is that you use a low-cost general circulation model called SPIDI, and they use that as your physics-based model, which is a low-cost physics-based model, and they apply a correction using machine learning to the output of the low resolution or the low cost GCM to obtain an ML estimate at short intervals of time. And what they see is that, sorry, yeah, I think there's a question. I'm just gonna keep this for later, but yeah. Yeah, and what they see is that a hybrid approach that combines a physics-based numerical model of the atmosphere with machine learning produces more accurate forecasts of most atmospheric state variables than the host GCM for the first 7 to 8 forecast days, which is a really nice, interesting result. I highly recommend that you check out the preprint that's been posted. And in sort of conclusion, the role of machine learning might not be immediately be as a direct replacement for physics-based models. And ML working in conjunction with a physics-based numerical model is a really promising area for research. Initially, the role of machine learning might be most promising in performing a lot of auxiliary functions, such as ensemble generation and data assimilation to assist physics-based numerical solvers to either reduce the computational cost or improve the accuracy of existing physics-based models. With that, I want to thank my collaborators, Sanjeev, Zongi, Ashish, Kamir, Thorsten, David, Karthik, and Anima. Also on the CFE project, Mustafa, Emmanuel, Mark Day, Wahid, who's the group leader at NERSC, and Peter Harrington, who has helped us with a lot of discussions. Also want to thank Istvan, Troy, Alex, Chishin, Brian, Michelle, and Ed, who worked with me during my grad school work on lot of different projects. And yeah, I think I've probably finished like 5 minutes early, but I would like to ask if there are any questions. I see there's a few in the chat. Yeah, I think I see that Naveed has a question. Would like to just say it out. So.
Yeah, hi. So yeah, I mean, I think in your conclusion slide you touched on that, but this time stepping and then using the machine learning model to nudge your trajectory back to the ground truth reminded me of what in climate models call state estimation or data assimilation. So
yeah,
I was just I didn't even have a question. I was just like urging.
Yeah, it's
you
a really
to,
good point, though. I mean,
but you did, I think. Yeah. But.
I agree. Yeah, that's a really good point. Yeah. Any other questions?
Hey, Jaideep. Great presentation. So I'm wondering, you may be already doing this, but can you enforce conservation laws, like to make sure that when you add a correction to velocity field, that it would satisfy the continuity equation or other things?
Yeah, and that's actually what I'm working on. I have not been able to do that just yet, just because the output of the solver differs in very like small magnitudes from the conservation laws, while still being not acceptable enough to like sort of fluid. If you're doing a resolved fluid dynamics simulation, for example. So it's in that region where it's like difficult to treat it just because it's so small. With machine enforcing those constraints is really hard, but it's not small enough that we can completely ignore it. But I think that's a really good question, and I'm working on it. I just haven't hit upon the right solution yet.
So early on, you talked about reservoir computing as kind of a pretty important way forward, right? I think that was kind of some of the earlier slides.
Mm-hmm, mm-hmm.
So, I mean, I still remember those papers. The performance were absolutely outstanding, right? It was definitely doing better prediction over multiple happen of timescales.
Yeah,
it's kind of almost shocking when we think about chaos. So, I mean, did you continue pursuing those lines, especially as we've been discussing a lot generalization and different regimes and different flow. And do you have a feel for why did it do so well, and what kind of approaches we could think about as we move forward?
That's a really good question. I mean, reservoir computing has, I think, a lot of like nice results, especially on like these toy problems that I demonstrated in several of those papers. Also, like as I mentioned, a lot of the work that my collaborators have done since then. Like I don't know if Iswan and Troy are at the meeting, but definitely feel free to reach out to them. And the issue that I found like recently is that there's a lot of like nice scaling properties that these GPU capable models, such as like Fourier neural operators or even convolutional neural networks, have. And I am trying to exploit these right now, just because it's difficult to scale reservoir computing. It's difficult to scale any machine learning model in some sense, but yeah, especially at the resolution that we're trying to model the fields at, which is 0.25 degrees, or hopefully even higher if possible. I mean, if we can get access to data sets that are at a higher resolution, then with reservoir computing, I mean, a lot of the like parallelization will have to be done by hand, basically, and it's difficult to run them on GPUs, which is not to say that there's not applications for those kinds of models. There's a lot of great work being done in that area as well, and I don't think anyone has like sort of settled on like what's the best model yet, and I think it's still a very sort of ongoing field, field of research.
Anyone else? Yeah. Questions for any other parts of the day, maybe, since we still have a fair bit of time. Or any comments? Relatively quiet.
I see someone has a raised hand.
Oh, there is a hand up. Oh yeah, Doc can go for it.
Hey, yeah, thanks. Really nice talk. I'm just kind of digesting a lot of the stuff I've seen for the first time. So just going back to the first set of work you showed, forecasting the atmospheric state in the high res era 5.
Yeah.
I just primarily at the moment had some technical questions about the neural operator you use. So what truncation did you use for the in Fourier space, and then also what loss did you use?
The loss was just a simple L2 loss. We are experimenting with a lot of different truncations, but in the sort of the hyperparameter called the modes hyperparameter, in these simulations is set to 32, but we are still experimenting with a few different hyperparameters for example the width, which is the hidden space, which determines the hidden space dimension, and right. Effectively what we find is that the larger the model and the more data it has, the better it works so far. So like the goal is to just go to more data and more bigger models. Yeah,
I mean you have enormous compute. I mean 256 A100s just blew me away, but I guess you just have to. Is the answer here more brute force? I mean, you mentioned the smaller scales, and I guess you could just go to, a longer truncation or so, or you could, and with the loss, the smoothing I noticed as well as you go later in the video. That's what.
Yeah, certainly. I mean, not just even later on. I mean, in the first time step itself, you encounter a lot of smoothing. Like as soon as it makes the first prediction, you can see that the results are smoothed out. So that's something that we are definitely working on trying to fix. And as far as like whether brute force is the answer, I mean, I don't think we know. I mean, I'm sure there's like a smart solution here, which is why I sort of like brought up the sort of hybrid modeling work, which if we were able to like if we were able to put together a sort of a combination of like models, which is like a low resolution forecast model along with machine learning, then that would be really nice. But it's just I mean, I don't know what the right answer is, but I think both avenues sound promising.
Yeah, no, fair enough. Have you tried this approach with Weatherbench? I haven't seen anyone use neural operators on Weatherbench yet, but you're kind of benchmark where you're at.
Yeah, I think that's a good point. I mean, the Weatherbench benchmark is like excellent. I mean, like there's some really nice work that's on the Weatherbench GitHub, and all the papers that have come out that have used the Weatherbench benchmark, and like we certainly hope to like compare the Z500 and the geopotentials and the temperature fields that are included in that benchmark with that. Right now, the focus that I'm looking at is like Weatherbench is at like I think either somewhere between like 2.5 or 1.5 degree to 5 degree resolution.
2.5, yeah.
Yeah. And what we're trying to do is like for example, for these like wind speed forecasts, I mean it's nice to have like higher resolutions. So that's what the focus is on right now. But I think concurrently it would be nice to like see what where we are at with those benchmarks as well. And this is definitely work in progress where we're trying to achieve that. Yeah.
No, that's really cool. Thanks.
Thank you.
One more here, Anish.
Hi, Jaideep. Thanks. Very nice set of works. My question is related to your work with the nudging, where you use the high resolution to estimate the correction made, and also related to like real data assimilation, where we have observations but sparse in space and time, that we don't have the full field of circulation, for instance, whereas in your case, you do have the full field to estimate the correction everywhere.
Right.
So have you thought about or worked on problems where you have data but sparse in space and time, and how do we estimate the corrections if you don't have the full field, right?
Yeah, I mean, I think that's a really good point. I mean, not in this work, I haven't tried to do that, but there is a lot of like sort of Ashish has done some related work on like sparse data sets with data simulation and machine learning. So I would definitely say that get in touch with him, and he's but it's a really interesting and important problem, I think.
Great. Thanks.
Thank you.
Can I? Sorry, just doesn't help.
Go for it, Duncan, then I go after you on the system side.
I was just curious. I just realized I don't know how much training data you needed for the high-res simulations.
It's so far, like I've been using like 50,000 samples, so it's like roughly 40 years of data at 6-hour intervals. But
For
you know, there's yeah.
At the full quarter-degree resolution.
Yeah.
Okay.
And I think, you know, there's like, it's just that, you know, it's a lot of data, and like ideally we would like to go to like hourly resolution and more variables. Yeah, as long as we have compute.
I'm just checking I'm on the same page for this. I'm talking about this MLPD hybrid thing now. So the
that's that one is at a lower resolution. That's like 512 by 512 resolution. That's yeah.
Exactly, but how much of those? Because you have to do those some of those high-res simulations to learn this.
Oh yeah, certainly. I mean, you need to do a lot of the high-res simulations. It's about like 50,000 snapshots again to train the model. But I think the issue here is that, I mean, I had these as like backup slides, but basically, if you try to do it with simply like a convolutional neural network, then what we found was that the prediction like sort of fails. Like for the same amount of training data, if you use the same size model and try to train on simply a purely data-driven approach, then we get some pretty unstable results after like 100 time steps, which is, you know, 100 autoregressive time steps is a lot of time steps. So whatever you do, if you were to compare it to basically just a pure ML approach, then you get like way worse results than the hybrid approach, essentially.
Yeah. Okay. Oh. Yeah. I mean, I guess it's just an interesting question, right? From a computational expense point of view, how you trade off these expensive training runs to, you know.
Yeah, definitely. That's a really good point. I mean,
thanks.
Yeah, thanks. So I had another question actually related to the coarse resolution model plus kind of correction. I mean, same thing a little bit is how much data do you need and how far into the future, you know, your prediction, how skillful when you do the correction. So is there a relationship between the amount of data and then the timescale of horizon?
Right. I mean, I haven't like explored that relationship very carefully, but the basic idea is that, you know, the amount of data you need is less than what you need if you were to do a pure machine learning prediction. So if the comparison is to pure machine learning prediction, then, you know, you need a lot less data than you would with that. And as far as like the forecast horizon is concerned, I mean, your prediction does get worse after a certain amount of time, and definitely. I mean, it's especially like because of this extra sort of small amount of energy. After like about 500 time steps, you know, your prediction looks a lot worse than what your numerical model can do, basically.
Any final comments? Oh, there is something else. Still Duncan? Or no? Karthik, do you want to say it out loud if you're up?
Yeah, sure. Can you hear me?
Yeah, we can.
Great, thanks. Yeah, I just wanted to add a couple of comments to what Jaideep said regarding the two questions. One is on the fine scales and the other on increasing the horizon of prediction. On the fine scales, I think Jaideep mentioned this, but when we move to hourly data, when we train on hourly data, which the Aero 5 has, we're likely to resolve the fine scales better. I think one of the reasons why we're smoothing out the scales is we're taking too large a jump. The second is on the prediction horizon, and this is based on some preliminary work with Ashish and others. We can optimize for multiple time steps at a time. So trying to predict not just one time step ahead, but multiple time steps. So in this case, it would be, say, an hour, 3 hours, 6 hours, 12, 14, or sorry, 12, 24, and so on. So that sort of multi-time step optimization would also likely improve the ACC over a longer horizon. We've explored some of that too.
Yeah, thanks a lot.
Thank you.
Karthik, is that when you say you over multiple time steps, is that in the same way that they do for MetNet? So you literally have a time horizon as an input parameter that you then can just run inference. So you just put in a different input parameter, you get a different output forecast.
Not quite. You train it to predict simultaneously multiple time steps, and then you combine that in inference.
I think there's a paper by Jonathan Wayne, if I'm not mistaken, that does something similar. Yeah.
Cool. All right. Yeah, I'll check that out. Thanks.
Okay, perfect. Thank you very much again for your talk. Let's thank the speaker again.
Thank you. Thanks a lot.